Fundamental quantities are quantities that are independent of other quantities. So that is, they do not depend on other quantity. So example of fundamental quantities, let's say we have quantities, we have unit, and we have symbol. We have symbol. So example of fundamental quantities are, the first one is length. It is measured in what? Meter. We have mass, measured in what? Kilogram. Kg. We have time, measured in seconds. Yes. We also have temperature. Temperature measured in Kelvin. We have amount of substance, or number, amount of substance, mole. This amount of substance is also called number of elementary particles. And we have luminous intensity. Luminous intensity. Luminous intensity. We also have current. Luminous intensity is measured in candela. CD. Current is measured in ampere. Capital letter A. The first three fundamental quantities, the length, mass, and the time, are the basic fundamental quantities. So they are the basic fundamental quantity. So when we get to dimension, so we use the dimension of this length, this mass, and time. We use it in dimension of derived quantities. Derived quantities. Derived quantities are quantities that are dependent on fundamental quantities. That is, they depend on fundamental quantities. So a derived quantity can be obtained by multiplying. Either you multiply one fundamental to another fundamental, two or more fundamental quantities, or fundamental quantity times fundamental quantity. It will give you a derived quantity, or fundamental quantity times fundamental quantities times fundamental quantities. It will still give you a derived quantity. That's how we get derived quantity. Or also fundamental quantity times derived quantity, two or more, it will still give you fundamental derived quantity. So that's how we get derived quantity. Or by division. By division, that is, when we have fundamental quantity divided by fundamental quantity, we will get a derived quantity. Or derived quantity divided by fundamental quantity, or fundamental quantity divided by derived quantity, you will surely get a derived quantity. That's it. We surely get derived quantity. So a derived quantity can be obtained by either multiplying or dividing two or more fundamental quantities, one fundamental quantities and one derived quantity, or two or more derived quantity. Dimension of derived quantities. If a quantity can be measured in length, mass, or time, so the quantity can have dimension. That is, so if we have quantity, let's say area is measured in meter square, right? So area is combination of two fundamental quantities, length times breadth, and you know that this breadth is also in meter. So we have what? Meter multiplied by meter, which equals to meter square. That's how we get the. So since this is in meter square, so the dimension will be what? Meter is length. So length, right? Put your square. So this is the dimension. Application of indices in derivation. In the derivation of derived quantity, we use some indices law. Like for example, the product law. Let's say we have a raised power b multiplied by b, a raised power c. So the law of indices states that when they have the same base, so you write one base and you sum up the power b plus c. So we use the product law. For example, in area equal to what? Meter, no, let's say length times length, and this length is in the power of 1. So we say L equals to what? Since they have the same base, 1 plus 1, which equals to what? L is power 2. So we also use it like when we have volume, we have, and the dimension for this is the dimension for area. So that's the dimension. So we have volume, we have length times breadth times height. So length is measured in meter. Since they have equal base, so we have m is power. This one is just power 1. We have 1 plus 1 plus 1. That's how we get meter cube for volume. And this meter is the unit of length. So we write length and the cube. So this is the dimension for volume and this is the unit for volume. So this area, we have length. The unit of length is meter. So we have 1 meter square. So when we have to calculate anything that has area, so the unit will be what? Meter square. And for volume it will be meter cube, unit of volume. But the dimension of area is this and the dimension for volume is this. We also use the division law of indices. Let's say we have a raised power b divided by a raised power c, which can be written as a raised power b over a raised power c. So when we have something like this, when the bases are equal, we just write one base. So raised power b, you subtract this, the numerator, the power of the numerator from the power of the denominator, which is b minus c. So this is the law. So we apply it to the derivation of derived quantities now. So let's say we have density. So the formula for density, first write the formula, which is mass over volume. So volume. So now write the unit of mass, which is kilogram, kg, over volume. Unit of volume is meter cube, that is length times breadth times height, meter cube. So applying the law of indices here, this place we will not apply the division law, we apply inverse law here. So the inverse law is, let's say, 1 over e equal to a raised power minus 1. So and when we have 1 over a all cube, so it will be equal to a raised power minus 1 raised power 3, so it will be a raised power minus 2. So we cannot apply the division law because they don't have the same base. So what we do is we split this, which can be written as kg multiplied by 1 over meter cube, and this 1 over meter cube can be written as meter raised by minus 3 from this law. So combining both, we have kg meter cube, right? So this kg meter cube is the unit of density, unit of density. So the kg per meter cube is the unit of density. So we can write the unit of density like this: kg per meter cube. So this kg is measured in, it is the unit of mass. So to get the dimension, just write this kg is the unit of mass in capital letter M. So and this meter is the unit of length in capital letter, so we put raised by minus 3. So this is the dimension of density. So note that dimension is always in an enclosed bracket like this. So that is the dimension for density, and this is the unit of density. So now we can apply the division law. Let's say acceleration equals to change in velocity over time, or change in velocity over change in time. So first thing we have to do is we have to get the dimension or the unit of velocity. So how do we get units of velocity? We know velocity equals to displacement measured in meter over time measured in second. So velocity will be meter times this 1 over s. Velocity will now be meter. So this 1 over s can be written as s raised by minus 1. Since we have this, so we insert it here. We have meter per second over, this is measured in what, second. So here we can split. We now have meter times s raised by minus 1 over s. So here we can apply the division law since they have the same base. So how do we apply it? We just say this, take it as 1, so minus 1, applying the law. So this numerator will subtract this. The power of this is 1 minus 1. No, is it like that? Yeah. So this will be what? S is by minus 1 minus 1 minus 2. So now meter per second square. So this is the unit of acceleration. So how to get the dimension for acceleration? We just say meter is length, second is time, capital letter T, then minus 2. So this is the dimension for acceleration. So we apply the division law, the inverse law here. So to get the dimension for force, we know force equals to mass times acceleration, right? And we've gotten the unit of acceleration to be meter per second square. So the unit of this mass is kilogram. Then we apply kg. So kilogram times it will give us what? Kg meter per second square. So to write the dimension, just kg is unit of what? Mass in capital letter. meter length, capital letter S, time is minus 2. So this is the dimension for force, and this is the unit for force. This is the unit dimension. So work and energy have the same unit, they have the same dimension. So let's say work or energy is equals to what? Force times distance. Force times this distance. So we've gotten the unit of force. The unit of force is kilogram meter per second square. So times this seconds here. So we now have kilogram meter. S is power minus 2 plus 1. So we have kilogram meter per second minus 2 plus 1. Yeah, I think it should be like this. S power minus 1. S power minus 1. Is it? No, there's a mistake here. So distance is a meter, not second. So we have times m. So here we now have kilogram raised by 1 raised by 1 we have meter square per second square here. So this is the unit of work or energy, also or call it joule. Yeah. So to get the dimension will now be into bracket kg meter, this length square, this time t raised by minus 2. So this is the dimension for work or energy. So the last one we'll be doing is power. Power is equal to what? Work done or energy expended over time or per unit time. So since we know our work done is this kilogram meter square per second square, so divided by time s. So to write this, we apply law of indices division method. We now have kilogram meter square s is per minus 2 minus 1, so it will be s is per minus 3. So this the unit for power. So and we know that unit for work is joule, right? So divided by, so we can also call it, we can also say or joule per second. So this is the unit of power or this. So the dimension of power, this is the dimension of what? Work. The dimension of power will now be equal to what? Meter L square t raised by minus 3. So this is the dimension for power. Please subscribe, like, and also comment.